Hi, welcome to chapter 18, ethers and epoxides. Okay, remember this is a recorded lecture. My name is Ramon Rios, I am professor in organic chemistry, and this recorded lecture, in any case, want to substitute your attendance in the lectures. Okay, remember that at Khalifa University, the attendance to the lectures is mandatory. Okay, what we will do in this chapter, we will talk about the naming of and properties of ethers, and then we will talk about how to synthesize ethers. Basically, what is an ether? An ether is a compound that the main functional group is a carbon bonded to an oxygen bonded to another carbon. Okay, this structure. Basically, we can have two alkyl substituents, like for example here we have two ethyls in each side of the oxygen, or here we have an aromatic ring and an alkyl in the other part of the oxygen, or we can have a cyclic compound where the oxygen is a part of the cycle. Okay, how we'll name it these compounds? Basically, what we have to do is to check both parts of the ether. Okay, if we take the oxygen, okay, we separate the two parts of the ethers. And one way to do it is we check the first part as a substituent, that means this will be a methane, that means if it's a substituent, it will be a methyl. The other part, okay, is a substituent, that means will be a terbutyl. And then we put these names in alphabetical order, and no, this will be isopropyl, not terbutyl, isopropyl, and then we add ether at the end. That means that this will be isopropyl methyl ether. Here we have another example, we do exactly the same. Remember, this is a benzene, that when it's a substituent is called phenyl, that means will be a phenyl methyl ethyl ether. Remember that ethyl has priority because the alphabetical order is first. Ethyl phenyl ether will be this final compound. Okay, this is one way to do it. The other way is that we can use the ether as a substituent, and then we will say the name with oxy at the end. For example, this is a benzene, okay, and we have two methoxides, two CH3O in each part of the benzene. That means that this will be para dimethoxy benzene. Okay, it's dimethyl, and then we add oxy because we have an oxygen. Here, for example, we can say that this is, we can use this as a substituent, and this will be a terbutyl. That means if we add oxy, it will be a terbutoxide, terbutoxy. Okay, then we only have to name this. This will be cyclohexane, the double bond will be the main group, will be a 4-terbutyl, if it's this is the main group, this will be position 4, 4-terbutoxy, sorry, 1 cyclohexane. Okay, here we have the problems 18.1, we can do it. This compound, okay, this compound, we can do it by the first method. We separate both sides. Okay, if we separate both sides, we have isopropyl in one side and isopropyl in the other side. That means that this will be a diisopropyl ether. Okay, this we can do the same. This side will be a propyl, and this side will be a cyclopentenyl. That means that this will be cyclopentenyl propyl ether. In this case, for example, we can use the methoxide case, and this will be a 1,4 or 1-bromo-4-methoxy benzene. Okay, or para-bromo-methoxy benzene. Here we can use also the oxy system, and this will be a cyclopentane, cyclohexane, because we have a double bond, cyclox1n, or 1 cyclohexane, and this is a methoxy. That means 1 methoxy is in position 1 because it is the same than the double one, 1 methoxy, 1 cyclohexane. Okay, and finally we can use this. This is a ethyl in this part, and in the other part we can see that is a isobutyl. That means that this will be isobutyl ethyl ether. Okay, remember that isobutyl or ethyl, isobutyl will be first because we only consider the B. This is isobutyl ethyl ether. Okay, we can use always, of the two possibilities, to use oxy or to use ether at the end, the one that we want. I recommend to use what is easier for you. What are the properties of the ether? Basically, the properties are based in its functional group. We have a carbon, oxygen, carbon. The oxygen has 2 pairs of electrons. Okay, that means the hybridization of the oxygen is sp3. For this reason, the separation, the angle between the 2 carbons will be around 109. In this case, 112, because the pair of electrons are slightly smaller than not a substituent. Okay, but it's around 109. For this reason, because we have an oxygen that is more electronegative than a carbon, we will have a density positive charge on the carbon and density negative charge over the oxygen. That means that this compound will be polar. Okay? But in this case, opposite to the alcohols, we don't have hydrogen bonding. That means that ethers will always have a slower boiling and melting points than alcohols of the same number of carbons, and will have bigger boiling and melting points than the corresponding alkane, because in this case we have dipolar moment. Okay? Here you have a list of different boiling points and melting points, boiling points. You see how an ether is higher always than the corresponding alkane. Okay? How we can synthesize ethers? Well, the synthesis of ethers, there are 2 ways. One is the Fischer synthesis, okay, that is based in an acid catalyzed reaction. In this case, we have to use an alcohol, we add acid, and what is happening? Something very similar that we saw in the case of the alcohol when we want to transform in a chloride. We protonate the alcohol in order to get water. The water is a very good leaving group, and then because this is a very good leaving group, another molecule of the alcohol can attack via SN2 to this protonated alcohol, and we generate the ether, protonated ether, that we lost the proton in the next step, to form the final ether. Okay? As a general rule, when we have a compound, organic compound that is positive, is charged, what we will do in the next step is losing, if it's charged positively, we lose a proton, a hydrogen plus, in order to generate the non-charged compound that is the stable compound at the end. Okay, this is one. Of course, this method has several drawbacks. The main drawback is that only works with primary alcohols, okay, that are the same alcohol in both sides of the ether. Why? Because when we protonate, when we add acid to the alcohol, and we have 2 different alcohols, we can protonate one or the other. We will never know which alcohol we are protonating. That means that, for example, if I am using methanol and ethanol, and I add acid, what I will get is the mixture of methanol with methanol, that means dimethyl ether, the mix plus ether with ether, diethyl ether, plus methyl ethyl ether, or ethyl methyl ether is the correct name. Okay, that means I will have a mixture of products. In order to avoid this mixture of products, what we can do is to do the Williamson ether synthesis. double alternator synthesis using an alcohol and an alkyl halide, and it's going through a SN2 reaction. Basically, we start with an alcohol, okay? We add a strong base, for example, sodium hydride is a very strong base and it's not nucleophile, that means it's a perfect base. Okay, we are forming the alkoxide, as you can see here. This is a nucleophile, and then this is attacking an alkyl halide, SN2 reaction, and we get the final ether. Okay, the only complication of this methodology is that we have to be wise in order, when we have the ether and they ask us which are the starting materials, we have to put the allyl chloride in the compound that is easier to do, in the part that is easier to do a SN2. Okay, for example, we have butyl cyclohexyl ether. Butyl cyclohexyl ether is this. Okay, which part will be easier to do SN2? Obviously, this will be easier than do SN2 in this position because it's primary, this is secondary. That means what I will do is to start from the alcohol of the cyclohexanol at a base, for example, sodium hydride. I make the alkoxide, and then this is attacking the alkyl halide. I put iodide because it's the best leaving group. Remember, we form and destroy the bond at the same time if it's an N2, and I get the final compound. Okay, always when I cut the molecule in order to see how I can synthesize this compound, I will put the alkyl halide in the compound that will give me an easier SN2. Okay? And good. That's all for this chapter, very, very short. Remember to do the problem session, the problems that are questions 1, 2, 3, 38, 39, and 40 of the chapter 18 of the book. And please read the book, chapter 18, points 1 and 2. Thank you very much for your attention, and see you in the next lecture.